Voila. On operando insight into structural disorder in battery electrodes. I think I had structural disorder as a description of my working methods once in high school, but looking forward what you have done. Thank you, Dorothy. The clicker is that. Oh, you can have it.
Thanks a lot for the introduction, and thanks very much for having me and for the invitation. It's really a pleasure to speak at this hallmark of European battery science. That's the word that comes to my mind. So I will talk about the work that we do on structural disorder in battery electrodes using operando techniques, so understanding how disorder affects the battery and how it forms as the battery is cycling. And first, a few words about me and where I'm from. So I am from Denmark, and more precisely from the red spot there, so that is Aarhus University, which we see here. So the green park here is Aarhus University. I think I will switch this one off. Very good. And we are at the Department of Chemistry. I'm a chemist and a crystallographer. So what you will be seeing in my presentation is a lot of structures. I hope you can bear with that. And I have the joy and the privilege of leading this new research center, which is called Center for Sustainable Energy Materials, where we study different energy materials, so materials that can convert energy. And we focus on disorder as a design tool. So we want to understand structure, and disorder, how it affects the performance, and hopefully we will learn how to control it. And within the center, in my own group, we focus on battery materials, and our main focus is on electrode materials. Then we have other activities feeding into this, and of course we also do quite a lot of method development, a lot of work at synchrotron facilities, neutron facilities, to become better at achieving information under operando conditions. So I will focus on disorder. As I said, I will talk briefly about what I mean when I say disorder, and then I will talk about how we study it, what methods we use, and then I have a few short examples before we will take a little bit more of a deep dive into layer transition metal oxides, where we will focus in particular on the role of iron. And towards the end, that is where it may become a little structurally nerdy, but that is what I do. So I want to start with this animation that you have probably seen many, many times. And I think that what you see in this animation probably depends on what part of the battery you are working on yourself. And what I see mostly are the ions moving through the structures of the solid state electrodes. And having ions which are charged and take up space, it's a physical object that has to move through these structures. That is a challenge, right? And only when this is efficient, time and time and time again, do we have an efficient battery. So therefore, this is, of course, very important. And if we look at the classical battery electrodes that we utilize in lithium-ion batteries today, we see that in the layered materials, this migration of the ions happen in 2D, in the layers. In the olivine, the LFP, it happens in one-dimensional channels. And actually in the spinel structures, it also happens in channels, but in all 3 dimensions. So of course, the long-range structure, the crystalline structure, is really important for this migration. But we also need to look at the local scale. So it's quite well understood now that if an ion move, and if you look at the right side here, move from the position I in the lattice, and wants to move out of the material, it has to go to another side in the structure. And it does so by jumping through an interstitial and into the next side. And the energy required to make this jump really is affected by what sits in the surroundings. So of course in the nearest surroundings, so here the oxygens, but also in these gate sites. And therefore the local structure and any disorder that may arise is very important for how efficient the ions can get in and out of the structure. And another important point is that as we have this movement where we have the electrons going in and out of the electrodes and the ions as well, we have two processes going on. We have oxidation and reduction of species in the host lattice. So that change, of course, the ionic radius of those species, but also the electronic structure. So it changes their preference sometimes for what they want to have in their surroundings. And also, we have, as I said, the intercalation of the active ion, and that takes up some space and carries a charge. And these two processes together, they bring about a structural phase transition. Sometimes they can also bring about a chemical reaction, but what I will focus on is mostly structural phase transitions. So it means that we can have a fully crystalline material, but as we go on about cycling the battery, we can have formation of disorder. So if we look at how it looks during the electrochemical cycling, we can have a crystalline material, so fully ordered, that remains that way throughout cycling. We could also have an amorphous material, like glassy carbon in sodium-ion batteries, and that will remain amorphous. But we can also have formation of disorder. And in some cases, this disorder can happen irreversibly, so we will never get back to the crystalline state. So we start cycling the battery, we reach a disordered state, and then we stay there, but actually, in many cases, the battery can still cycle very well, even though we are in a disordered state. And we can also have reversible disordering, where we have a crystalline material, and then either at the, say, fully charged state, or at some intermediate state, we have a heavily disordered phase, and then the crystallinity comes back again as we keep on cycling. And from sort of a fundamental perspective, this is in itself extremely interesting how such a process can happen. So I want to now tell you a bit about how we go about studying these processes. And of course, we use electrochemistry. And I think in contrast to many other fields, we actually have a very nice advantage that the materials we look at, they are perturbed by electrochemistry. So in many other fields, right, you look at something changing as a function of temperature. And of course, when you change the temperature, something happens, but you don't get any output from the temperature alone, right? But here, having the electrochemistry means we have this extra probe that we can actually also use in our interpretation of how the structure change. Then we use, of course, diffraction, so X-ray, neutron diffraction, electron diffraction, more and more, which will tell us something about the average, so the crystalline part of the structure. Then we use also X-ray absorption spectroscopy, where we can probe changes in the electronic state, so the oxidation state of the elements that we probe. So that's typically the transition metal elements. And then we also use a lot of total scattering, so also known as pair distribution function analysis. And this is what can give us insight into the local structure of the materials. And since this is likely a technique that lesser of you are familiar with, I want to spend a minute on that. So when you do a total scattering experiment to get your pair distribution function, you basically do like a normal diffraction experiment where you shine X-rays onto your sample and you collect the scattered signal. But here we just want to have quite high data quality, and we want to have data at very high scattering angle. And then we take that data and we do a few mathematical corrections, so like a background subtraction that needs to be made very carefully. And then you do a Fourier transform that brings you from the reciprocal space, so the space we normally look at when we deal with crystallography, and into real space. And that gives you actually something that you can very easily or intuitively interpret. Because the pair distribution function, as you see here, is kind of like a statistical function. So here we have a probability, and here we have interatomic distances. So you can see here, the first neighbor is the blue distance, the second, the red, and so on. And if we have a simple monoatomic chemical or compound, then the peak area would also correspond to the coordination number. Of course, we typically don't have that. And with this, we can actually fit a structural model. So when we have a pair distribution function, this is how it looks in reality for a quite crystalline compound. Then we can, just as if we do a refinement of powder X-ray diffraction data, so Rydberg refinement, we can take a structural model and we can refine that against the data so we get structural information out. And also then, if we have something that is either nanoparticles or very disordered, amorphous, then we can see now we have well-defined correlations to much shorter distances because it becomes disordered, but we can still use a crystalline structural model. We simply just cut down the coherence length of that, and that means even if something is not crystalline and we don't get diffraction data that we can use for an analysis, we can use pair distribution function analysis. So to turn these methods into operando methods, where we look at what happens as the battery is cycling, we typically use a cell design like this, where you build your battery stack and put it into the cell, and then this cell is equipped with carbon windows, so they are conductive, and so carbon is quite a light element, so it allows us to shine an X-ray beam through it, and then we can collect the signal on the other side here. So we put that in the beam. Typically we go to a synchrotron for this because it means we can have a better time resolution, we can get higher quality data, but actually to a higher extent we can also do this at our in-house facilities because you can get like a silver X-ray tube with a rotating anode. That means you have a high flux and quite a high X-ray energy. So it becomes easier and easier. But we place it in the beam, and then we perform the electrochemistry that we want to do. And then at the same time, we collect the signals from the X-rays, and we can do this in the three modes that I talked about. So we can do diffraction, we can do total scattering, so that's PDF analysis, and we can do the absorption spectroscopy. And this we can all do on the same electrochemical cell, which is really an advantage because it allows us to correlate things more directly. And then we can also do the top two at the same time and the bottom two at the same time. And this is how it typically looks at the synchrotron. So we typically cycle sort of 5 to 8 cells in parallel, because typically battery experiments are not that fast. So we shoot at one cell, move the stage, shoot at another, and so on. And here I also want to put in sort of a brief word of caution. Something that I always say is that when you do this, you really have to be aware of beam damage. So these images here show electrodes that have been cycled during the 3 bottom one during an operando experiment, and the top one without any X-ray exposure. And you can clearly see that where the beam has hit the sample, so here and here and here, the electrochemical reaction is lagging behind. So we are at a much lower state of charge where the X-ray beam has hit the sample. So it means that exactly where you're probing, you will actually not be seeing what is really going on. So one important thing is to go up in energy as high as you can, because then the absorption will be lower. But also we tend to do this, that every time we come back to the cell, we shoot at a different position. So it means that we really try to limit this. Yes. So before I get into the layered materials, I want briefly to mention 2 examples where we utilize PDF analysis. And that's because in the layered materials, PDF analysis is not so great. I will come back to that. But I thought it was nice to see that what this technique can do. So this is a study that we did, now already some years ago, where we studied vanadium pentoxide during lithium intercalation and deintercalation. And when you do the first lithium intercalation, it goes through a series of crystalline to crystalline phase transitions. But then the last one, from the gamma to the omega, it disorders quite a bit. But we still have, so if you look at the black curve here, you see we still have quite nice diffraction. But then as we take lithium out again, so we discharge, then we lose almost all of the Bragg intensity. So it was really, this phase was completely unknown. And then we switch instead to the PDF. So here we have the operando PDF, and I have extracted some patterns, and now we have data where we can fit different structural models and build these models and figure out what's going on. So just in short here, we start with this layered vanadium pentaoxide, and then as we discharge, go through all the crystalline transformations into the omega phase, and the omega phase is actually a disordered rock salt. We didn't think so much about that at this time, but it is, and we could even show how the local ordering in the octahedrous, how the dispersion were. And then as we come back, so as we charge again, we form this beta structure. And what is really interesting about this, so first of all, it is very disordered. So the order only has a length scale of about 10 angstrom. So that's quite small. But we can also see that it actually consists of sort of a hybrid between this layered structure that we had in the beginning and these blocks that we had in the disordered rock salts. And now I have been saying to some of my students that I think actually we should pick this up again, because it's very interesting in terms of the disordered rock salts that you could end up in such a hybrid structure here. So another example that is very recent, we are still working on this, is a study of phosphorus graphite composite anodes. And red phosphor is a little bit like, so silicon for lithium-ion batteries has a huge capacity, but also a big problem with the volume expansion. And phosphorus is a little bit like silicon, but just for sodium-ion batteries. So we can get a huge capacity, but it has a very large volume expansion, meaning that it dies after a few cycles. But then it has been shown numerous times that if you add some carbon source, you can stabilize it. So again, just like silicon, where you need to add graphite. So we did the same. We added graphite and studied this, and we got quite good theoretical capacity. We do need to use high energy ball milling, which also means that you have a structure here that is highly disordered, simply, at least for the graphite part, from smashing it. So this is what the diffraction pattern looks like. It's very hard to analyze. So instead, we turn to the PDF. And here, we learn a very interesting thing. So I have been teaching first year inorganic chemistry for many years. And every year I'm saying to the students that this is the structure of red phosphorus. And maybe it is, but what we had bought as red phosphorus actually came out having a mixture of these two structures instead. So this one is actually known as violet phosphorus and fibrous phosphorus. And we can also see from the Raman that the graphite during the ball milling has heavily exfoliated and become quite defected. So as we cycle it and as we insert sodium, we can immediately see actually that the crystallinity increases. And we form this sodium-3 phosphor compound. And we can cycle between these states, but we do indeed see that after around 100 cycles, it still dies. And that is observed several times in the literature. And so what we have also been doing, and these are quite recent results, we have also moving into to X-ray computed tomography, together with Alexander Matic from Chalmers. And what we can see here, so down in the very bottom where you have this little red line, that is actually our phosphorus electrode. And we can see as we sodiate it, we can see that it does indeed expand quite a lot. And if we look closer at this region, so here we also have the desodiated state again, we can see that the voids that we have here in blue, they are actually really sort of being filled out as we have this huge volume expansion. And as we come to the desodiated state again, so here I have a zoom, we can see that already after one cycle, these voids or empty spaces, they are really growing. So the electrode is very fast cracking. Good. So now let me come to the layered sodium transition metal oxides. And here the focus for us has really been on sustainability, to trying to see how are these materials behaving if we try to go for sustainable or say low cost compositions. And I was actually very happy to see this excellent seminar from the Battery 2030 Plus that was aired about 3 months ago. And I can recommend this. It's a very nice lecture. So here, the presenter showed sort of the most common cathode materials in sodium-ion batteries. And here we are on the layered materials, and you see for all of them we have iron and manganese, except for the bottom one here. And this is really what we have trying to focus on, and And to keep it simple, we also cut down the composition to those two elements. So a little introduction to the layer transition metal oxides. So they come in two forms when you synthesize them, an O and a P. And then they have a number. If you're not familiar with this, don't think about the number, doesn't matter. But we have O, meaning that sodium sits in an octahedral coordination, and we have P, meaning that sodium sits in a prismatic coordination. And this is actually very important for how these materials behave. And another thing you could sort of say, okay, so we have used layered materials for decades now for lithium-ion batteries. Why do we have to study them all over again for sodium? And this is sort of a simple proof of that. So you can see here that the electrochemical, the potential curve, becomes quite different. So when you exchange sodium and lithium. And for the sodium one, you have much more sort of bumps, which indicate that you have much more phase transitions going on. And also you can say, okay, so if you look up layer transition metal oxides in the literature, I don't know how many papers you will find, but a lot. And they all have a little bit different composition. And why do we need to study all of them? And it's a similar argument. So here we have in orange the one based on nickel, and in green the one based on nickel and titanium. So their phase behavior really change a lot when you change the composition. So here is our little material map. And as I said, we start with this mother material where we have 50-50 iron and manganese. And then we can synthesize them in P and in O. And it's quite simple. You mix these compounds, you bake it. That's more or less it. And if you tune the amount of sodium that you put in your starting composition, so what you put in your furnace, then you can tune how much P and how much O you get. So that is pretty straightforward. And today I will focus on the O materials. And here we have a series where we have different iron content. So here is sort of medium iron and then high iron over here. And even without being an expert on diffraction, you can easily see that there's a dramatic change when we go above 0.6 to 0.7 iron. So we want to explain this difference. And we will focus first on the first charge, because that explains a lot of this. And if we look first on what happens generally in these materials. So in general, if we go down in potential, so we discharge all the way, we typically have formation of some like monoclinically distorted structure due to Jahn-Teller distortion of manganese 3+. I will not really be focusing on that today. But instead, and this is where it's interesting for me, because when we go up in potential, we see that the layers begin to glide relative to each other. So these begin to slip, and they do that to sort of counterbalance two effects. So one is the repulsion between the sodium, and the other is the repulsion between the oxygen between the layers. And quite often when this layer glide happens, it happens in a not very orderly fashion, so we have stacking faults, meaning that some layers may be P-type with prismatic coordination, and others may be O. And that is, of course, where the disorder comes in. If we also look a bit at the redox processes that can happen. So down at low potential, we have the manganese redox, 3 to 4, and a bit higher up, the iron, 3 to 4, again. And yeah, that is sort of, you can say, standard redox. And then a bit further, we have actually another process that is not a redox process, but it is driven by the redox. Because when we begin to take sodium out of the structure, we create vacancies in the sodium layer. And that vacancy is super tempting for an iron 3, because the iron 3 really wants to move to a tetrahedral position. So iron 3 has a strong preference for sitting in a tetrahedron, and when there becomes space in the sodium layer, it can do that. And iron 4 will not migrate, at least not to a very large extent, because it doesn't have this preference. And it's also important to note that this migration can only happen when we have an O layer. Because if we have a P layer, the prismatic layer, there are no tetrahedral sites in such a layer. So it has to go into the O layers. So, and that creates, of course, an iron vacancy in the transition metal layer, and it has been debated quite a lot whether this makes oxygen more prone to oxidize, because, of course, what we have at high potentials is oxygen oxidation, where we can go from O2 minus to O minus, and we could even have formation of molecular oxygen. And here, the fact that we lower the energy density of the oxygen has also been suspected to make iron more prone to migrating. But again, it's debated. So I want to make also a comment on what effect these processes has on the structure, on the unit cell. And I just needed to check the time. That's fine. So in the A-axis, that is really an expression for the size of the transition metal layer, because the A-axis describe the size of the planes, right? So that means that when we have reduction or oxidation of the transition metal layer, that layer will change the size, its size. So therefore, we can in many ways see this, the change in the A-axis as a sign of transition metal reduction or oxidation. Then if we look at the C-axis, so that's the distance, right, between the layers, which is an expression, you can say, of the repulsion between the layers. That repulsion will increase when you begin to take out sodium, because then the oxygen repulsion is less shielded by having a positive sodium sitting in between them. So it means that it will increase. But if we have the iron migration, so the iron going down into this tetrahedral site, then it will actually contract, because this tetrahedral site is quite small compared to sodium sitting in an octahedral site. And these effects here, they have quite a dramatic effect on the performance. Because if we look at the iron going into the tetrahedral site, so it will sit in the pathway where sodium wants to migrate. It will also contract the layers, so it will really hamper the iron migration. Also, when iron moves into this tetrahedral site as iron 3, it is not very likely to be oxidized to iron 4. So it also cuts down on the capacity available in the material. So here we have cyclic voltammetry data for these 4 materials with different ion composition. And to sort of assign these redox processes to make sure what corresponds to what, that is where absorption spectroscopy becomes very useful. So here we have the absorption spectra for the manganese edge and the iron edge. And then we take the first derivative, and that allows us to extract the edge position. And the change in the edge position is an expression for a change in the oxidation state. So now we can see that we have an area first where manganese is active, and then iron, manganese on the top becomes almost flat. And then we have up here an area where you can see there is a bit of change both in manganese and in iron. And this is an expression for oxygen redox, because that induces a small change in the structure of the, you can say, all of the transition metals. So not just iron and not just manganese. And of course, it's also confirmed when we come to the diffraction. So it now allows us to assign redox processes here. And we can extract a bit of information from this. We can see that as we go up in iron, so first of all, the upper potential peak, so the peak that contains both a contribution from iron redox and oxygen redox, is actually pushed down in potential. And the other one maybe a little bit up. And we can also see that as we go up in iron, we get sort of a shift in relative capacity from this low iron peak up to the peak that contains both the iron and the oxygen redox. And this is important because it means that when we, at higher potential, we will still have more iron 3 available for the migration. So now I come back to this data, because now we can begin to look into it. And you see that when we are at these high potentials, both here and over there, we lose intensity. So the line, for instance, go from being red, so that's highly intensive, to fading out. And that means we lose crystallinity. And so the first thing we did, that was not maybe so smart, was to do PDF analysis. And the good thing about doing it was that we could see that we didn't have formation of anything else. No amorphous phase or no you can say unexpected local ordering. But since this is just stacking faults, so we all the time have O or P type environments, it actually means that the PDF does not tell us very much for the layered materials. So if you're doing layered materials, maybe it's not the technique to go for. But instead, we can refine these stacking faults. And we use the program Faults, which was developed by Montse Casas-Cabanas. I know you're here somewhere, but I don't see you. Oh, you're there. And we invited Montse and some of her team up to give us a workshop about using this, and that actually kickstarted all of this work for us. And when you use faults, you build structures a little bit like Lego bricks. So it's a very fun way of dealing with structures. So here we define one layer that is the transition metal oxide and the sodium oxide layer. And then we define a vector that allows us to stack the Lego bricks in different manners. So we can stack them in such a way we go from an O type to an O type. And we can go from an O to a P to a P, and a P to an O. And that's the 4 vectors that we need. And we can then refine the probability of these layer transitions, and we can get the ratio of the O and the P layers. We can define the thickness of the different layers, and to some extent also the sodium and the iron occupancy in the different layers. And now comes a few little bit busy slides, but I will try to point to where to look. So these are the data or the results that we get when we use our faults model on all of our operando data. So it allows us really to follow the evolution of these stacking faults very closely. And now we look at these medium iron compositions. And we see that first we have a very very crystalline to crystalline transition, where we go from O3 to P3. So all of the layers glide into P. And that happens just to minimize the repulsion between the sodium ions. And then we go on, and not a lot of stuff is really happening until we get to the P3 to the OP2. And when this happens, we actually see that now we have a dramatic change, because now we have this huge decrease in the z-axis. So it means that the layers really come closer to each other. And we can see from down here that this contraction actually happens in the O layers. And if you remember a few slides back, I told you that the iron can only migrate into the O-type layers. So it shows that at this point we have iron migration. We can also see now up here that at the very highest potential, our A-axis, so it goes down, 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 because iron is being oxidized, and then it flattens out. And that happens because now it switches to oxygen redox instead. And this, I mean, you can say whether or not this is linked directly to the iron migration is a little bit hard to say with the time resolution we have here, but it looks like it happens sort of a little bit after. But what we can say is that the iron migration happens sort of immediately. So when this OP2 phase nucleates, it is there. Yes. So now we come to these high iron content material. And you can say from a sustainability perspective, this is where it becomes very interesting. But unfortunately, it doesn't go so well. But we now see that up here, we begin to have formation of P-type layers. So the material really wants to go from the O to the P. But then it stops. It cannot. And that is because, and now we have enough iron to actually refine how much iron is sitting on these tetrahedral positions. We can see iron begin to migrate. And as soon as an iron sits in a tetrahedral, in an O layer, it cannot glide into a P layer anymore, because it sort of is pinned down or blocked by this. And actually, we have this happening in two steps here. And these two steps follow exactly the two sort of big increases in the capacity that we see from a CV. So it means that we first have one decrease in the sodium occupancy, or creating vacancies in the sodium layer, allowing iron to migrate, and that is then happening again. And then only again at the very highest potential, we see the oxygen redox kicking in. So it means that these are not necessarily correlated, right? If iron migrates at a low potential, it cannot promote oxygen redox. Yes, so here we have a little phase map. And what I want to emphasize here is that what sort of saves, you can say, these lower iron content materials from ion migration. That is formation of the P3. So we have this quite long range here where P3 is stable. And when we have this complete P3 structure, iron cannot migrate. So it cannot migrate before we have formation of the OP2. So that sort of saves it, and this actually tells you probably that if you want to go very high in iron, you need to find some way to make these materials prefer the P3 structure to prevent the migration. I also want to touch a little bit here upon the reversibility, because you can see as we go back, so as we charge again, as we discharge again, we see that the iron migration goes down to 0. But actually, looking at the absorption spectroscopy, we can see that it is not completely reversible. So we need to look at the pre-edge here, because that tells us if we have a tetrahedron or not. Because the pre-edge here will show us anything that is so-called non-centrosymmetric. So if we have an octahedron, an ideal octahedron, we will not see anything in the pre-edge, but a tetrahedron will show up. And we see here that as we have the charge state, we have a quite big peak, and that actually remains a bit in the discharge state. So it is only partial reversible. So now I want to move on a bit to the second cycle, and here we will focus on the 0.5 material, because you see, when we have charged one and discharged again, and we go into the second cycle, we now have this X phase. And this has been called X for quite some years, because it was not really clear what this phase was. So we want to understand what is the structural nature of these high potential phases, and also what causes this difference between the first cycle and the second cycle. And maybe we can also relate this to this capacity loss that we always see in the first couple of cycles for these materials. So we have already talked about the first cycle. So we go completely into the P3, the one that saves us from the early ion migration. Then we have these OP2 structures, and then we come back to the O. And then as we cycle on, we come to the X. And as you can see down here for the second cycle and on, then we all the time go between O3 and X, O3 and X, O3 and X, and so on. So we never come back to P or this OP2. So if we first look a little bit closer at this OP2 phase and look into the results of the stacking faults analysis, then we see that the OP2 structure consists of about 50% O layers. So that is actually equivalent of crystalline OP2, because there you would have O and P all the time. But we can also see that we have about a little more than 30% chance that if we are in a P layer, then the next one will also be P. Or if we are in an O, the next one will also be O. So it means if we simulate how such a crystallite or particle will look, we will have some domains that are O-type and some that are P-type. It is not completely stacked in a well-ordered manner. Yeah, so we have a second of these OP2, it's the same story. And then I want to mention that when we come back to the O3, it actually goes fully back to O. It's not like there are stacking faults left behind or anything. but there's some iron left behind, but there are no stacking faults left behind. So now let's come to the X phase and look at this. So again, here I have the refinements of the operando data from the faults analysis. And we see, just like for the high iron materials, that the material really wants to go toward P, but then it gets blocked. And that is most likely because we have this small amount of iron left, right? And the fact that we never come to the P3, that means that the ion migration, the early ion migration, can happen. The floor is open, you can say. But let's first look at the nature of the X phase. So we have this highly disordered phase here. And when we do the faults analysis, we can now see that it's very O-type. So more than 70% of the layers are O-type. But we can now also see that these stacking probabilities, so the probability that if we are in a P, and the next one will be P or O to O, they are now quite different. And especially for the O, right, we now have more than 80% probability that if we are in an O layer, the next one will also be an O layer. So when we simulate the X phase, we have much larger O and P-type domains. And this, of course, explains quite well why the crystallinity is so poor, because it's very, very disordered. And I want to emphasize again that whenever we come back to the O, the pristine state or the discharge state, it is not stacking faulted. So in that sense, it regains the crystallinity. But we can see, as I said, that when we go up in potential here, we have a decrease in the C layer that is linked to a decrease in only the O layer, so that is indicative of the ion migration. There was some. So here is, again, a summary of these phase transitions. I think I have already explained it. And the important point is really that the lack of the P3 phase, that is what enables this early ion migration and what also will enable it to build up. Because we see when we compare the cyclic voltammetry collected over multiple cycles here, we can see that the ion activity goes down. And we can also see actually that it shifts quite dramatically to lower potentials. Whereas the first one here moves upward. So again, or at these low potentials, the fact that we have less ion activity means that we have a lot of iron 3 available for the migration. And then we have taken a material here from batteries cycled a number of times, taking the electrode out, and we have done the faults analysis at the charge state. And what we see is that the X phase become more and more O-like. So it tells us that there are more and more O layers being pinned by the ion migration. And we can also see a little bit of a correlation here. I'm not saying it's a strong evidence, but we have this early capacity loss, which actually fits with both the change in redox potentials plateauing out and also the structural buildup of the O-type. So the final thing that I want to mention very briefly is that we are also looking into putting in sort of the third transition metal here. And we have probed a range of elements. And then we again have cycled number of times and done the false refinements on the chart state. And we see actually for all of them, when we cycle multiple times, we always end up in this X state. And it seems that lithium can indeed reduce the speed of getting to this X phase, but still that is always where we end up. So in summary, I hope that I have convinced you that in the layered materials, the phase evolution and the disorder formation is controlled by sort of competing sodium-sodium and oxygen-oxygen repulsion reduction, and these redox-enabled transition metal migrations. And that whenever we have oxygen layers available at a certain level of sodium-ion vacancy formation, then we will have ion migration. So what can we maybe do to tune this? There are different things that has been done, so you can lower the voltage window. That, of course, also lowers the capacity. You can substitute cations, maybe. Maybe there's also a sort of a viable route in designing disorder. So you have a material that from the get-go is disordered and somehow more will stabilize the structure. And also maybe anion substitution, as you do in the disordered rock salts. And also I want to say that structural disorder is definitely not accidental, right? Sometimes we think of disorder as being random and accidental, but it is happening or occurring in a very distinct way. It can be diagnosed and predicted, but we really need to combine tools and preferably under operando conditions to probe it. And with that, I just want to thank you all for listening.